This is video 12 of the GCSE Physics video series, all about wave properties. And so we're starting a whole new topic on waves, completely different. We finished with forces now, forces are done. We're now talking about waves. Lesson 72, the nature of waves, starting with the basics, and there are different ways of describing waves. We could describe the wave by the type of wave. So waves can either be mechanical waves, that means that there is something physically moving, or an electromagnetic wave, which means that there is an oscillating electric and magnetic field. Blimey, I've started to talk about waves, I haven't even told you what a wave is yet. Well, it's easier to explain what a wave is with pictures, which you can see running here. They're ways of transferring energy, or momentum, or information, or even force, without transferring matter. Matter can move, but matter isn't transferred from one place to another. It just oscillates. So a wave isn't a physical thing, it's just a mathematical way of describing the motion of matter, or electric fields in the case of electromagnetic waves, that causes this transmission of energy from one place to another. It's a little bit complicated, but don't try to think of waves as a thing, a wave. Think of it as a way of describing this flow of energy, this flow of momentum, without actually transferring matter, because the matter just oscillates. So mechanical waves is matter oscillating, particles vibrating. You've got to have matter for there to be mechanical waves. You can't have mechanical waves transmitting energy through a vacuum. Electromagnetic waves, on the other hand, they can travel through a vacuum, and they are just electric and magnetic fields. Electric fields, we've met the idea of electric fields in video number 4, where we introduced the idea of electric charges. Around all these charges, there are these fields. If I shake a charge around, then the field around it oscillates. And if I place a charge in that oscillating field, that charge feels a force up and down because of the field oscillating. But you can have the field oscillating without the charges there, so that's why you can transmit electromagnetic waves through a vacuum. And we'll talk more about electromagnetic waves in the next video. So that's one way of describing waves, the type of wave we're talking about. Of course, there are other types of waves. We've got probability waves, which we'll cover a little bit in A-level. We could even talk about how currency flows on the stock market, and we could describe that in a wave way. The idea of a wave is just a way of mathematically describing this oscillating nature of things. The other thing we can do is describe the topology of the wave. That's just a fancy way of saying the shape of the wave, what the wave looks like. And the two topologies that we're interested in are transverse waves and longitudinal waves. Best explained with pictures. So you have a look at these two animations on the right. I've got this regular grid of squares, and if I shake it to the side, as I have done with the case of the transverse, then you can see that the bars that are horizontal here, they don't move at all. But the vertical bars, they clearly oscillate to the left and right, and then back and settle where they started. In the case of longitudinal waves, I'm shaking this grid vertically, and so you can see the vertical lines don't move. But the horizontal lines, they kind of get bunched together and then spaced out again. And then they settle back where they started. So we have our two different types of waves. The better way of describing these sorts of waves is to look at the direction of oscillation and think about it in terms of matter, in terms of mechanical waves. It makes it a little bit easier to see what's going on, not least because you can't have electromagnetic waves that are longitudinal. They just don't exist. So let's do all of this in terms of mechanical waves. We are oscillating, in both of these cases, we're oscillating matter. We're shaking matter. We're causing matter to vibrate. In both of these cases, the wave is being transmitted from the bottom of the screen to the top of the screen. The energy of the wave is going from start at the bottom to the finish line at the end, at the top. In the case of the transverse wave, the oscillations, the vibrations, the matter is being displaced perpendicular to the direction that the wave is travelling. In the case of the longitudinal wave, the matter is being displaced parallel to the direction that the wave energy is travelling. The wave is travelling vertically. In the longitudinal wave, the oscillation is also vertical. The wave is travelling vertically, but in the transverse wave, the oscillation is horizontal. I've deliberately chosen to arrange the transverse and longitudinal wave diagrams here this way round, because usually they're drawn the other way round, and students start saying things like transverse waves, the particles oscillate up and down, and longitudinal waves, they oscillate left and right. Well, that's only true if the wave is travelling from left to right or from right to left. So the more general phrasing here, perpendicular and parallel, is important. But don't just say transverse waves are perpendicular too. What? No, what you mean is, in a transverse wave, the oscillations of matter are perpendicular to the direction that the wave energy is being transferred. And with a longitudinal wave, the vibrations of matter are parallel to the direction the wave energy is being transferred. So we can describe waves as being mechanical transverse waves or mechanical longitudinal waves. Or we could say longitudinal mechanical waves, transverse mechanical waves. We can also have transverse electromagnetic waves, but you can't get longitudinal electromagnetic waves. They just don't exist. So here's a picture of a different type of wave. This is a complicated one because each of these dots represents matter, and you can see that there is an element that is, the wave energy is clearly going from left to right. There's a part of this wave, an element of this wave, which is transverse. The wave is going from left to right, and this top particle is demonstrating up and down motion. So there is an element of transverse wave in this, but there's also longitudinal wave in this. This is a mixture of both. Water waves are a mixture of both. Often examiners actually just want you to say that's a transverse wave. It's not quite as simple as that. I mean, this actually is a bit fictitious anyway, because this shows the matter becoming more or less dense, and it doesn't quite work like that. So water waves are actually quite a bit more complicated than we tell you in GCSE level, but we'll say they're transverse waves to keep it simple. So here are some examples of transverse and longitudinal waves. Transverse waves, electromagnetic waves, so light is an example of that. Water waves, we're going to say they're transverse for our exams, water ripples. Seismic waves, so that's earthquakes, that sort of thing. There are transverse waves that are seismic waves. There are also longitudinal waves that are seismic waves. Sound is an example of a longitudinal wave. It's an example of where air pressure increases and decreases. If you look where the longitudinal wave is moving, let's just focus on this longitudinal wave, you can see there's a region where it becomes more dense and a region behind there where it becomes less dense. So that where it becomes more dense, we call that a compression, and where it becomes less dense, we call it a rarefaction. Those are terms that are unique to longitudinal waves. Air, being a gas, can be compressed, so you can have longitudinal waves in air, you can have sound waves in air. You can also compress to a certain extent within solids, because you can get the oscillation causing regions that are more dense, and even in liquids. But air is a really easy example to see how we've got regions that could be more dense, regions that are less dense. And so we have these more dense regions called compressions, less dense regions called rarefactions, and together both of those are indications of longitudinal waves, because you don't get them for transverse waves. Right, let's move on then. That's the basic nature of waves. Let's move on to some of the properties of waves. Lesson 73, the properties of waves. So I've got two diagrams here, and I've done this deliberately. One of them is time on the x-axis. The other one just says direction of wave propagation. So that is a distance along the x-axis. Time along the x-axis on the graph on the left, distance along the x-axis on the graph of the right. Let's suppose we're watching something oscillating on the surface of water as ripples are moving across the surface of the water. Perhaps we're using a ripple tank like this to produce ripples by placing something that vibrates on the surface of the water, so we get these nice ripples such like that. And if you have a light source above, you can see the ripples projected below. The ripple tank is a required practical. Making use of a ripple tank to make measurements and choosing sensible instruments and strategies to make those measurements is a required practical at GCSE level. Well, if I were to watch a little speck of dust or something on the surface of this water, what would I see it doing? Yeah, I'd see it moving in a circle, but let's ignore the motion horizontal for a moment. Just look at the vertical motion. What I would see is over time, the particle would ascend, then descend, then ascend, then descend, then ascend, then descend. So if I plotted a graph of the position of the particle over time, what would I see? I would see that. I would see the picture on the bottom left. But I could also look at the whole water, not just that speck, but the whole water at an instant in time. Perhaps I take a photograph and just have a look at the water. And I can see the water itself over that distance has a high part and a low part, and a high part and a low part, and a high part and a low part. So whether I am looking at a particular point in space and how the surface of the water position changes over time, or whether I'm looking at a particular instant in time and how the surface of the water position varies over space, will depend on whether I get the graph on the left or the graph on the right. In both of these graphs, the maximum displacement of the surface of that water, this is maximum displacement from the equilibrium position of the water. That's the height the water would be at the surface if there were no wave. The equilibrium position is exactly halfway between the top and the bottom of this wave. The amplitude is what we call that maximum displacement, and that is the case in both of these graphs. The graph in what we call the time domain on the left, and the graph in what we call the space domain, or the temporal domain on the left, and the spatial domain on the right. Let's name some other parts of these graphs. The top bit I keep referring to, we call that the peak or the crest, and that is true for both types of graphs. The bottom bit we call the... try again. The bottom bit we call the trough, and that is true on both of these types of graphs. So why am I focusing on the two types of graphs? Because of this feature. The distance from one peak to the next, or from one trough to the next, is the same distance from peak to peak as it is from trough to trough. That distance is called the wavelength. But on the time domain graph, the temporal graph over here, what is a distance along the x-axis is representing a duration, an amount of time. And there's a special name for the time from when the particle... Remember, we're looking at a single point in space, a speck of dust on the surface of the wave. The time from when it's at the highest point to when it returns to that highest point, or from when it's at the lowest point, the trough, to when it returns at the lowest point, the next trough, that time we call the time period, or sometimes we just call it the period. So we've got some definitions here. Amplitude, maximum displacement from equilibrium position. Frequency, haven't defined that yet. That is the number of waves passing a point per second. If we are watching over time, we can see how many waves pass per second. If we plot a graph like this, if it was 1 second interval along the x-axis, we could count how many full waves there are, peak-to-peak waves that there are within that time interval. 1 second is probably not very long, so we might measure it over a minute, and then, we want the frequency. We'll divide the number of waves we see in a minute by 60 to get the number of waves we see in 1 second. So that's what frequency is. Actually, we're doing it per second. You could describe frequency as waves per minute, but we don't. When we say frequency, we're using the unit hertz, and hertz is another way of saying waves per second. That's all hertz means, waves per second. Wavelength, we've defined, distance, wave travels in one period, where a period is the time it takes for the distance of a wave to be, the wave to travel one wavelength. So those two are linked together. But another way of describing the wavelength is the distance between adjacent peaks, or the distance between adjacent troughs. So the period is another way of saying the time it takes for a wave to travel one wavelength. It is also calculable. You can calculate the period as the reciprocal of the frequency. That's what it is. Period we measure in seconds, frequency we measure in hertz, which is the same as waves per second. So the reciprocal of waves per second is seconds per wave, which is what a period is. The number of seconds, the amount of time for one wave to travel, or for the wave to travel a distance of one wavelength. This equation here at GCSE level is often called the wave equation. It's actually not a wave equation, but that doesn't matter. At GCSE level, we'll call this the wave equation, and we'll fix that later on in A level. Wave speed sometimes is expressed as a c, particularly if we're talking about the speed of light. All wave speeds are speeds, but not all speeds are wave speeds. So here I'm using a v, the general letter for a speed. Notice none of these are bold, they're all scalars. Actually, we could make these vectors. Lambda can become a vector, but we'll leave that. That's a problem for A level, when we start looking at two-dimensional and three-dimensional waves. So v is our wave speed. It's equal to our frequency multiplied by our wavelength. I love this equation because it's got a Greek letter in there. With lambda, it's got F, which is a great letter because it's the tallest letter, and I somehow find that quite relatable, myself being ridiculously tall, 2 meters tall. It's a very simple equation. It's a simple three-term equation, so I really like this equation. It also has a special place in my heart because when I first met this equation, it must have been in year 9 when I was a child, many years ago now, this was the equation where all of a sudden my understanding of physics switched on. I don't know why. There's nothing special about that equation really, but when I first learned how to rearrange equations and how to relate the idea of distances to times to speeds, this equation switched the switch and meant that I understood physics. And it was all uphill from there. So very, very, or downhill from there? Uphill. It improved from there on. But until that point, physics was just a mystery to me. This equation unlocked all of physics for me. I don't know why. It's just the way some brains work. At some point, something will trigger something and you'll get it. And that happens to everyone. It happens at different times. And you don't know what it'll be that will trigger it, but it'll happen to someone. It'll happen to everyone if you just persist with physics for long enough. Let's move on to lesson 74. Lesson 74, we're now looking at some things that waves can do. Waves can reflect and waves can refract. Now, we do have to be careful because there are lots of very similar sounding words with very similar spellings. So, refraction and reflection, they sound similar, but they are definitely different words. There's 2 letters different, RA and LE, but do make an effort to spell these correctly. We don't usually care about spelling in physics, but do make an effort in this case to spell these correctly. Let's start by talking about some more parts of the waves that we can describe. So we looked at a wave in the last lesson, lesson 73, which was a single line with some sort of oscillation. If we actually consider the surface of the water, it looks like there are these little hills of water. And I've drawn red lines connecting the highest points of the water, and then down here would be these troughs. So we've got crests and troughs and crests and troughs and crests and troughs, and these will all move along like this. Wave fronts are what we're going to call these lines of these peaks in a two-dimensional wave, these lines of these peaks. There is a better definition of wave fronts. Wave fronts are points, they're what you get when you connect points that have the same phase, actually technically the same phase difference, but we're not going to go into that. That's an A-level topic. We're just going to visualize wave fronts as these points where the waves are all identical in nature. Everywhere where there's a peak, we're going to draw a dot, and we connect all these dots together, and we end up with these lines. So those wave fronts, lines of peaks, fine. We call these plane waves simply because the wave fronts are all straight. It's not always the case. Sometimes they're curved wave fronts if they are emerging from a point, which is, let's take water for example, a ripple spreading outwards, has circular wave fronts. But here we used a ripple tank to produce plane waves, straight wave fronts. Wave fronts are always perpendicular to the wave direction, the direction that energy is being transferred by that wave. So we can show diagrams where the wave is moving in a certain direction by indicating the wave fronts perpendicular to that direction. And that's what we can see up here and down here. Here we have our red lines. These are our wavefronts. And here we have these sort of blue bits. I've emphasized the color and rotated it all around here to make it easier to see. These white bars, they are wavefronts. They are progressing along as the wave moves. The blue line here and the blue arrow in this diagram down at the bottom indicates the direction that the wave energy is traveling. So waves can do three things when they're incident upon any surface. They can either be reflected or transmitted into the medium or be absorbed by that medium. So those are three things that waves can do. Now, we're not going to be too interested in absorption at the moment. We're just looking at reflection, and when we transmit into a medium, we may very well refract. Refraction. So refraction happens if the media are what we call different optical densities, if it's light. Not sure what the term we would use if it's water waves, but I'm going to have to stick with optical density and do it in terms of light because I don't know what else we would call it. So we would get refraction if the waves change speed. We'll talk more about that, I'm sure, at some later point. But if the wave changes speed, then it changes direction. So let's look at reflection to start with. This is not a change in speed. Reflection, we have our wave coming in. The wave fronts are indicated with these red bars. There's a point where the wave is incident, and then the wave reflects off like this. So you can see this wave front here. This wavefront here is already reflected, so that's why it looks like it's got this weird kink in it. And then the waves transmitted like this. You have to be able to reproduce diagrams like this for reflection of plane waves on plane surfaces, plane reflectors. That is what happens. Now, the angle of incidence, that is the angle between the incident ray, that's what we call this line here, which shows the direction the wave is traveling as it approaches. Assuming we're coming from the top left, I haven't drawn arrows on this diagram, but if we're coming from the top left, this is what we call our incident ray, a line showing the direction the wave energy is going, an arrow showing the direction the wave energy is going. That is our incident ray. If we measure the angle between that ray and the normal to the surface, remember normal is 90 degrees to the surface, we call that the incident angle. Let's get my pen out, see if I can draw without a ruler. This is not going to work great, but we'll do our best. This here is my normal to the surface. It's not bad. I'll label it N for normal. Don't normally have to bother. That there, that angle I've just drawn the curve on, that is our angle of incidence. I'll use the letter I for that. It turns out the angle of reflection, that is the angle between the normal and the reflected ray, is the same as the angle of incidence. The law of reflection, they sometimes call that. That is true for specular reflections. Recently produced a video where I showed that our students' understanding of reflection is wrong, usually, because it's taught in a quite sloppy way. I'm going to have to teach it in that sloppy way because it does get quite complicated how reflection really works, but that's fine. We can do that, we can get our GCSEs, and then we can go on and study more advanced physics later. So angle of incidence equals angle of reflection, fine. When we transmit into a surface, we are penetrating into that surface, we could have the wave change speed. So in this case, the wave slows down. You can see the wave is travelling slower in the second medium compared to in the first one. And if you look at the wavefront part that hits the medium first is slowed down first, but the wavefronts must cause continuous lines. They can't become broken. They can bend, but they cannot break. And so the only way to get the waves to travel slower in the second medium, while still having continuously connected wavefronts across that boundary, is to have the wavelength smaller. The wavelength peak to peak, therefore it's the distance between two wavefronts. And you can see the distance between wavefronts in the second medium is smaller than in the first medium. So the wavelength has reduced and the speed has reduced because the frequency stays the same. Because these wavefronts connect across the boundary, as many waves hit the top of this surface per second as emerge into the second material per second. We don't lose any waves. As many waves hit the top as go through into the second, go through into the bottom medium per second. Per second. So that is the same frequency in both materials. Lower speed, got to have a lower wavelength. How can we possibly have a lower wavelength in the second medium? We're going to have to bend those wavefronts along that boundary. Bit of a flabby way of talking about refraction. Again, actually, the mechanism of refraction is a lot more complicated than that, but this is fine for GCSE level in a sort of graphical way of understanding what's going on. It doesn't really tell us why it happens, it just tells us what does happen. It doesn't tell us, for example, why does the wave go slower in the second medium. But that's all stuff we can cover later in your physics education. There's a reason why topics like this find their way towards the end of the course. There are only 16 videos in this course, and we're on video 12. So when we talk about light, if a medium has what we call a higher optical density, it means that the light travels slower through that medium. Lower optical density, the light travels faster through that medium compared to the higher optical density medium. And so we refract towards the normal. Look at the blue ray. It gets closer to the normal if we are moving from low to high optical density. That's something that you ought to be able to remember. Now, with water waves, it wouldn't be very sensible to call it optical density, but it's the same principle. As the waves go into shallower water, they actually slow down, and that causes the wave fronts to change direction. Now, usually, if you consider water waves out at sea, and the seabed coming up until it's a lovely beach, the water's getting shallower and shallower as it gets closer to the beach, that's a gradual change, and so you wouldn't get this sudden step change in the waves. You would have a turning of the wave gradually, and you see that the wave fronts coming to the beach, usually pretty much the wave fronts are parallel with the beach. Well, that's why. It doesn't matter what the direction the waves are out at sea, they kind of turn towards the beach as the waves come in. Right, so that's refraction and reflection as an introduction. Don't worry, that will come up again when we talk about optics, which is in video 14, I think. Video 14, we'll talk about optics, and we'll talk about refraction and reflection in more detail. This is just a general introduction to those two concepts in terms of waves in general. So lesson 75, lesson 75, some more about waves. Don't know how useful this is, but here we go. This is a bowed ukulele. Some people call it a violin, but those people are losers. This is a bowed ukulele. And as the bow sweeps slowly across, and this is in slow motion, as the bow sweeps across the string, it causes vibrations to travel down the string, reflect off this bridge at the end, and then, I mean, that's not a bridge, is it? What is that? What do we call that bit there? Can't remember what we call that. The nut, that's what we call that. Reflect off the nut and travel back towards the bridge, where it reflects off the bridge and travels to the nut, and these waves interfere with each other. We can do something similar here with a signal generator connected to a vibration generator attached to a piece of string, and we can set up these vibrations on this string. It's a pretty standard lab experiment we can do. That's a one-dimensional wave. What we've got on the picture at the top is a ripple shown in a two-dimensional wave. So it originates in the center of this 2D grid, and the wave radiates outwards. There's a two-dimensional wave. The picture on the top right is an attempt to draw a three-dimensional wave. So there's something in the middle, perhaps this is a sound wave, and there's something in the middle producing this sound, and you can see it looks like something is radiating from the center. But if you watch a single particle, if you're good enough and you can watch a single particle, the particles are actually oscillating. They are not traveling from beginning to end. They are oscillating. It's difficult to see because some of them appear to go off the edge and then come back again. So don't watch the ones too close to the edge. So sound waves, vibrations in air caused by changes in pressure. Fine, we'll leave that as it is. They can't travel through a vacuum. If we get a bell jar like this, put a buzzer in it or something and attach it to a vacuum pump and remove the air, we'll hear the sound get quieter and quieter until it completely stops. And the sound completely stops because it's a vacuum. So you need medium to vibrate, to oscillate, in order for there to be sound. Sound waves can travel through solids and liquids as well, and they travel faster through liquids and even faster still through solids. So these are just examples of 1D waves, 2D waves, ripple tank for example, 3D waves, sound in a room. That's all we needed to show with this. We're going to move on now to lesson 76. I'm going to focus on sound waves in a little bit more detail. So sound waves. We've got an instrument that can hear, that can detect sound waves, a remarkable instrument inside our ear. We've got this outside bit, this auditory canal, which will channel, if you like, the sound waves. This is our pinner on the outside. The sound waves are going to come in. And then we've got this thing here. It's called the tympanic membrane here. It's also called the eardrum. Now, the tympanic membrane, the eardrum, is a thin layer of tissue that separates the middle ear from the outer ear. Now, this thin layer of tissue is all that separates those two regions. So if you were to suddenly increase the pressure outside, then you could actually damage this eardrum. You do have to be quite careful with this. It's very sensitive. So what happens if the pressure outside is higher than inside? Well, that surface area is the same whether you're inside or outside. So if the pressure outside is greater than the pressure inside, then the force pushing from out to in is greater than the force from in to out. That pushes the tympanic membrane in a bit. It pushes it in. If the pressure outside in the outer ear was lower than the pressure on the middle ear, then the air in the middle ear is pushing outwards more than the air on the outside. So that pushes the tympanic membrane out a bit. Now with a sound wave, as we saw in the last lesson, in lesson 75, the sound wave is caused by the pressure of air going from high to low to high to low to high to low. That's what's causing this transmission of energy we call a sound wave. Which means that in this region on the outer ear, just outside the tympanic membrane, if there's sound, the air pressure is going high, low, high, low, high, low, which means the tympanic membrane is being pushed in, out, in, out, in, out. Now, the tympanic membrane is connected to three bones, these three ossicles, the three bones inside our ear, the hammer, the anvil, and the stirrup, or the malleus, incus, and stapes, if we want to call them those. Those transmit this vibration to this instrument here, the cochlea. The cochlea has a oval window on one side, onto which we've got our stirrup connected, and the other side is an open round window. And it's, if you follow from one to the other, it's a tube that gets narrower, narrower, and narrower, and then wider and wider and wider again, but it's narrower and narrower and narrower, and it's just coiled up to save space. But it's just a tube that changes in diameter. And so if we've got a vibration on one side of that tube, it causes all of the fluid inside that tube to vibrate, to oscillate. Okay, super. So along the walls, the interior walls of that tube, which is all coiled up, there are hairs, cochlear hairs. Those little hairs can sway if the fluid is oscillating. And when they sway, when they oscillate, the louder the sound, the bigger the oscillation, the more they sway. So the louder the sound, the greater the amplitude of oscillation. As the amplitude increases, the sound gets louder. So it causes these cochlear hairs to vibrate a greater distance, more. The higher the frequency of sound, the higher the pitch of the sound, should I say. It means the same thing. The higher pitch of sound, the higher the frequency of the sound, the more frequently these cochlear hairs vibrate. Low frequency, they vibrate with a low frequency. High frequency sound, they vibrate with a high frequency. They are sending nervous signals or electrical signals to the brain via the cochlear nerve to say, where along that tube, that cochlea, the hairs are, and how much they're vibrating. Now, where they are, it tells you the frequency of the sound. Where the tube is narrower, higher frequencies make those hairs shake. But the tube is less narrow, lower frequencies. So which hairs shake tells your brain what the frequencies are. How much they're shaking tells your brain the loudness. And your brain does the rest of the work and turns that into what we would perceive as sound. Very, very clever. If the pressure inside becomes greater than the pressure outside, because let's say, for example, you go up a big hill, or maybe you are on an aeroplane where they reduce the pressure in the cabin a bit, still higher than the pressure outside the cabin, but they reduce the pressure inside the cabin a bit. Well, what happens then is your hearing becomes impaired. You hear more quietly because the tympanic membrane can't move as far because it's being pushed already, so it's got less movement it can have. So everything sounds a bit muffled. Sometimes you'll hear your ears pop, and that's where the eustachian tube, which is usually closed, it pops open just to allow air to get in to or out. If it's higher pressure inside, it lets the air out. If it's lower pressure inside this middle ear, the tympanic cavity, it lets air in. So you'll hear the eustachian tube just pop open, and that's when your ears pop. You should never pinch your nose and blow to try to make your ears pop, because what you're doing there is you're forcing the eustachian tube to open, but you're actually forcing whatever gunk there is in your ear, nose, throat system up into your ear, and that can become infected, and you can get a nasty ear infection. So you should never do that. Let it do what it's supposed to do. Usually you can force the eustachian tube to open a bit by chewing and exaggerating your chewing motions, because the tube is connecting your middle ear all the way round to your nose and everything else. Your nose is connected to your throat, so ear, nose, and throat is all part of the same thing. When people say their sinuses are sore, that's because of congestion in these tubes that connect the middle ear to the nose, to the eyes. It's all connected somehow. So that's how we detect sound. That's how it works. Now, because the cochlea has a certain size, a certain geometry, we are sensitive to certain frequencies of sound. In the same way as on a musical instrument, think of an example. Let's get my ukulele. On a musical instrument such as this, okay, if I don't know if you can hear that. Might be a bit quiet because the amplifier's not turned up very loud. But if I make the string shorter by fretting, higher pitch sound, and still shorter, high pitch, still shorter, higher pitched. So just like that, there are different pitches of sound that can be heard because the different lengths of the strings on an instrument. If you play a pipe organ, big pipes, deep sound, small pipes, high-pitched sound. If you play the flute or a piccolo, flute, certain pitch of sound. Piccolo, smaller instrument, higher-pitched sound. All different instruments. The bigger they are, the deeper the sound is. So it's the same idea. The bigger the part of the cochlear tube is, the lower the frequency that the hairs will shake at. But because of that, elephants, which have much bigger cochlea in their ears, they can hear much lower frequencies than humans can. Whereas animals like mice, they can hear in higher frequencies than humans can hear. So we have a range of frequencies over which we can hear, and it ranges from about 20 Hertz to about 20,000 Hertz. I mean, mine is significantly smaller than that, my range, because I'm in my 40s now, and so I have impaired hearing to a certain extent. In fact, because of my history of listening to heavy metal music very loud, my hearing is pretty terrible. But there we go. 20 Hertz to 20,000 Hertz is roughly the human range, but it's not the same sensitivity to sound across that range. We are most sensitive around about 1,000, 2,000, maybe even 3,000 Hertz. That's where the sound sounds louder. If we play sound of the same amplitude of all these different frequencies, it will sound to us louder around 1,000, 2,000, 3,000 Hertz. These different curves on this graph you don't need to memorize this, but these different curves on this graph are just different mathematical ways of trying to model the human response, the human hearing response. Where the higher up it is on the y-axis, the louder it sounds to us. And there's a really interesting scale on the x-axis. It's a logarithmic scale. So 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4. It goes up like that. But yeah, we can't hear above about 20,000 hertz. It drops off very quickly. We can't hear below about 20 hertz. It drops off too quickly. Below sort of, 40, 50, negative 40, negative 50 decibels of loudness, we can't really hear it. So that's our hearing response. Other animals have a bigger range of hearing. That's not the only thing that happens with ears, with hearing. We have also got animals that have adapted their ability to hear so that they can almost see with sound. Bats are a very good example of this, but let's focus on this sort of mammal, this underwater mammal. It produces a click within its skull, which sends out a sound wave through the water. Some of that sound will echo off if there are any fish it might be hunting, and it can then, with very, very sensitive, not using an ear quite so much, it uses part of its jawbone, which gives much bigger area to detect if there's this change in, this vibration in pressure, this sound coming back. It's called echolocation. So if a fish is a distance d away from the whale, the sound, let's say it travels through the water at a speed v, then the distance between the fish and the whale would be the speed of sound multiplied by the time it takes for the sound to get to the fish. But of course the whale doesn't know that the sound has got to the fish. It can only detect the sound when it reflects off the fish. So the fish is over here, the sound goes to the fish and back. So the time, it's very clever how they do this. They can somehow understand, the brain has understood that the time between when they send that click and hear the click, that time, if you halve it, that is the time that the sound has travelled to the fish. So d equals v times t, but this is half the time because it's the time it takes for the sound to get to the fish only, if we want to know that distance, which is half the time it takes between when you send the click and hear the click. So that's echolocation. That happens with very low frequencies, and whales can kind of tell when there's a school of fish somewhere, but they can't necessarily see all the fine detail on that fish. Unlike bats. Now, bats are able to spot flies and see flies, and it's possible that bats could even sort of detect face shapes from humans with their ultrasound, which is an incredible idea. So let's have a look at ultrasound, which is lesson 76. We said there's a range of human hearing. Sound, so acoustic waves that have a frequency above the range of human hearing, about above 20,000 hertz, we call ultrasound. The ones that are much lower frequencies than humans can hear, we call infrasound, but we're not focusing on them. So ultrasound is frequencies higher than humans can hear. If you use echolocation with ultrasound, because the wavelengths are much smaller, because the frequencies are much higher, okay, C equals F lambda, V equals F lambda. So as the frequency goes up, the wavelength goes down. That means that the reflections, much smaller wavelengths, we can pick out more detail from those reflections. Approximately, we can resolve detail approximately with the same size as the wavelength of the waves that we are reflecting. That's as a general rule. It's not quite like that, but that's a general rule. So the higher frequency sound, the higher resolution detail that we can identify, that we can see, in quotes, using this ultrasound. So that's why bats have such remarkable ultrasound. But we have developed technology where we can use ultrasound. On a very basic level, let us consider a sheet of metal. Perhaps this is a sheet of metal that's going to be made into the wing of an aeroplane. And it would be really lovely if we could tell if there were any interior cracks when we made that sheet of metal. Any interior cracks, as the airplane wing flexes, those cracks can grow and grow and grow, but because they're inside that metal plate, we can't see them, which means that by the time we realise they're there, is when the cracks have reached the surface and the wing's about to fall off. So we need a way, before we make our plane, of checking whether the materials we're using actually have any cracks inside them. And this is one way of doing it. This is what's called a transducer. It transmits and receives, sometimes it's called a transceiver for that reason. It, well, the transducer, it says here, just produces ultrasound waves, but that's not quite accurate. Transducer just changes energy, transfers energy from one store to another. But anyway, this is a transceiver. It sends and then detects ultrasound from the same instrument. The pink part here indicates the path of the ultrasound is travelling on the way down through this metal. Now, what we're going to do is we're going to produce pulses of ultrasound, just like the whale, pulses of ultrasound, very, very quickly. And we're going to plot on an oscilloscope, which is an instrument that shows us what the signal is, because we're going to take this ultrasound receiver. It's going to return a potential difference that increases when there's ultrasound. So we're going to put that into an oscilloscope. So when there is ultrasound detected, it produces a spike. And the first spike, that is because of the ultrasound we are sending. We're just detecting that straight back. Then there's a time delay. The x-axis of these oscilloscope screens is time. And then there's a second pulse. And that second pulse indicates that the ultrasound has travelled all the way down to the bottom metal part, reflected off that boundary and come back. Whenever there's a boundary between different media, there will be reflection from that boundary. And transmission, possibly, and absorption, possibly, but there will be reflection as well. So EP here, the time EP on the oscilloscope graph, is the time it takes for the ultrasound to travel from the top surface to the bottom surface and back to the top surface. Okay, so we could actually measure the distance on the oscilloscope screen and say that they can calibrate that and say it's to scale with the distance, the thickness of the metal plate. Now, as we move this transceiver over the surface of the metal, we might suddenly detect another peak. Now, if we detect another peak, that means there's some sort of fault within the metal, which is also reflecting ultrasound. And if we know the relative distance along the x-axis on the graph, which we're labelling D here, D compared to EP, we can use that to work out D compared to EP, the depth into the metal where the crack is. If the crack's quite close to the surface, I don't know, it might be fine. If the crack's right in the middle of it, that might be a problem. I don't know, I'm not an aeronautical engineer. Might be the other way around. But we can detect these faults within our material with this simple ultrasound. Right, well, that's a single ultrasound transceiver that's sending a single pulse blah, 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 over and over again, and it just tells us if there's a crack. If I get an array of these transceivers, an array of them, I can do something really clever, because the waves are going to be travelling down slightly different paths, then reflecting, and there's going to be a time delay. So if they travel down slightly different paths, there's going to be a time delay when they return. So I can use that to produce images inside the human body. This picture here is a picture of my daughter. And at the time when I'm recording this, she is 10 years old, but she was less than 0 when this particular picture was taken. With this picture, there is a transceiver at the top, which is sending out ultrasound, and it's reflecting off a boundary between different media and returning. And the dot is placed at a certain distance, radial distance from the top here. That's why it always looks like a bit of a cone when you see these ultrasound images. That distance corresponds to the time between when the pulse was sent out and the pulse was detected. So this to this structure here was a much smaller time before we got that echo back than this one here, which is a much smaller time than this one here. But any change in density of tissue will cause a reflection. So this transceiver up here, I think it was actually moving, but I can't remember. It's sending a pulse, detecting it, sending a pulse, detecting it, might have an array of multiple of these, and produces a much higher resolution image. Now, to get these higher resolution images, you've got to use higher frequency ultrasound, so there's a smaller wavelength. And the higher frequency ultrasound, the smaller wavelength you use, the better the detail you can resolve. You can now get what are called four-dimensional scans, where you can see movement in real time with incredible detail. You can see all the features of a fetus's face and hands and all the rest of it because of how our transceiver technology has improved. So it's just, but it's using the same principle, D equals VT over 2, but just improved technology, and so on. That's all that's happening. You can do it for looking for fetuses inside wombs, or you can look for kidney stones, or blah, blah, blah. There's lots of things you can do with ultrasound as a diagnostic tool. We use it in particular for looking for fetuses, and because ultrasound causes no harm. It's not like ionizing radiation, like an X-ray, which of course we'll talk about in the next video, or maybe the video after. No, the next video. It's not like X-rays. X-rays can pick out detail of where bones are and things because bones absorb the X-rays, but X-rays are ionizing, so it can cause harm. Ultrasound doesn't cause any harm at all. So it's a basic principle here. An audible echo, large wavelength, can only be used to locate large buildings. Okay, so if you clapped your hands or shouted or something, you'd hear an echo back. That's coming off something big because the wavelengths we can hear are reasonably large. And if you want to see smaller objects like fingers or noses, like this little nose here, or the jawbone here, if you want to see small features like that, well, then you're going to have to use much smaller wavelengths, much larger frequencies. And moving on to lesson number 78, which is the final lesson of video 12, lesson 78, seismic waves. So these are acoustic waves. They are matter, so mechanical waves. Remember our description of waves. They're mechanical waves, so they're matter that's vibrating in the earth for some reason. Now, what is that reason? Well, there's a number of things that can cause seismic waves. There are earthquakes that can cause seismic waves, where tectonic plates move past each other, and as they move past each other, they cause the ground to shake. Volcanic eruptions, yes, but also explosions. There's weapon explosions. It could be any sort of explosion can cause seismic waves. Meteor strikes can cause seismic waves. So anything that can make the ground shake can cause a seismic wave. And they are mechanical waves. Fine, okay. The point where the waves spread from, we call the epicenter. So on this diagram, this is a slice of the Earth. We are considering the epicenter to be here. And I've labelled that as 0 degrees, and I've orientated the image so 0 degrees is right at the top. This is the Earth, so it's about 6,400 kilometers in radius, as you can see there. And I've labelled 0 degrees, 30, 60, 90, 150, 180. So I've labelled the angles going around like this. I say I stole this off Wikipedia. It's used under Creative Commons license, so that's fine. Although irritating me that the 8 down here is upside down. I don't know why they do a bigger round bit on the top than the bottom. That's irritating me. But anyway. It's my problem to deal with. So we've got this picture here. If this is the epicenter and the waves are radiating out, then we can draw wave fronts for those waves. And those are these sweeping curves like this. Now, further up, they break into dotted lines and things. And that's because otherwise it's going to get really difficult to follow what's going on. But these sweeping curves are our wave fronts. And remember that perpendicular to wave fronts are the rays, in quotes. We can't really call them rays for seismic waves. We tend to call rays the lines that show direction that light waves travel. But I can't think of a better word for it than a ray. So this is an acoustic ray travelling from the epicenter. And that's these lines that radiate from the 0 degrees. And of course they are crossed by these wave fronts that you can see here. Now, what you'll notice is that they are curved. And the reason why they are curved is because the Earth gets more dense the deeper you go. The denser it gets, the faster the waves will travel. Mechanical waves travel faster in more dense media. If they travel faster, that causes them to refract away from the normal, which is why they curve in the way they do. And then they start getting shallower and they continue that curve. So that curvature of those rays is an indication of the changing density of the Earth's mantle. Now, there are different types of mechanical waves that travel through the Earth. There are waves that are longitudinal and waves that are transverse. There are also waves which travel along the surface. We call those L waves. It says long waves here, travelling slowest, only move through the crust. L can also stand for love waves, named after whatever the geologist was that named them. So L waves travel along the surface. I'm not particularly interested in them at the moment. I'm interested in the other two waves, what we call P waves, where the P can stand for primary or it could stand for pressure, and S waves, where the S can stand for secondary or it could stand for shear. P waves, pressure waves, primary waves, arrive first at a destination. So if you were stood over here at, let's say, 30, 40, 45 degrees, you were stood where my cursor was, and there was an earthquake at 0 degrees, then you would experience, first of all, the P waves. They would travel fastest, they would arrive to us first, and they are longitudinal. You would then receive the S waves. They would travel slower, so they arrive second, and then finally would get the L waves, which we're not that interested in today. So the P waves, if you look, the ray is coming up out of the ground at 45 degrees. So the P wave, being longitudinal, would cause the matter, that is, the ground, to oscillate parallel to the direction of that ray. In other words, as the ray is emerging out of the ground shakes up and down. That happens first. In an earthquake, everything jumps up and down first. Then there's a time delay, and the further you are from the epicenter, the greater the time delay. So by timing that difference, you can work out how far away you are from the epicenter if you know the speeds that the waves travel through the Earth's mantle. Then the secondary wave hits. The secondary wave is a shear wave, it's a transverse wave, so that means because the wave is coming up out of the ground, the matter shakes perpendicular to that direction, which is left and right. So everything falls off the shelves as the whole ground shakes side to side. That's what happens second. Okay, except there is an interesting thing that happens around this region here. If you are from the epicenter about, well, just a little bit less than 100 degrees around from the epicenter, to round about 100, so 110, 20, 30, 145 degrees from the epicenter, you don't detect any earthquake at all. Your seismometers, those are what we call the instruments that measure seismic waves, your seismometers show no detection of an earthquake at all. Seismometers can be very, very sensitive. Even if you don't feel the ground shake, the seismometer could. So your seismometers around this region detect no earthquake, but your seismometers around here do, and the seismometers on the other side of the Earth to the earthquake will also detect that seismic activity. Well, what's going on here then? Well, this is evidence for a sudden change in material density under the Earth, under your feet. But not only that, from about 98, 99 degrees around further, remember this is just a slice, so this is all the way around as well, you will detect no S waves at all. No S waves. There'll be no S waves. You can only detect S waves from 0 degrees to about 98 degrees. Now that's very interesting. You will detect P waves, and only P waves, when you are about, 145 degrees around 280 degrees, and remember it's a circle, so it's all symmetrical, on the other side of the Earth from the epicenter. You will detect P waves there, but no S waves. But you will detect P waves and S waves from 0 degrees to 98, maybe 99 degrees. So what's going on here then? Well, it turns out P waves can travel through liquids as well as solids. But S waves cannot travel through liquids. They can only travel through solids. To get an S wave, to get a shear wave, we have to have the matter pulling in such a way, acting like a spring, pulling the matter back where it was within that structure. Well, because with, let's take water as an example, when you push the water molecules, they move. They physically move past each other. There's no force to bring them back where they started. So you don't get those shear forces that are necessary for S waves to propagate. But you do get pressure waves where it gets higher pressure, which pushes against the bit the other side, and so on. So you do get longitudinal waves. You do get P waves travelling through liquids. But you can't get S waves. So that indicates that there is a region beneath your feet, and based on the curvature of these rays, you can estimate at what depth, about, well, was it? So 1,200, about 3,000 kilometres below our feet, where the Earth's material changes from being a solid, the mantle is pretty much solid, sometimes it's called a semi-solid, it's solid enough. It does flow, but ridiculously slowly, so let's call it a solid, to liquid, a true liquid, beneath our feet. About 3,000 kilometres below our feet, a true liquid. But not only that, we can detect differences in intensity of these P waves that we do detect, and use that and model what the rays would look like to create a model where the intensity we detect matches our model. And doing that, we have identified that there is also a region beneath, even deeper than that liquid region, where the Earth becomes solid again. Now, you don't have P waves, we don't have S waves detected from there because they don't pass through the liquid anyway. But what's happening here? Well, the outer part here, this is called the outer core. Okay, we've got the crust on the edge, then the mantle, then the outer core is liquid, the inner core is solid. We know the inner core must be solid because of all that weight of the material above it pushing down, pushes the liquid ion, even though it's at a higher temperature, it's at such a high pressure that it remains a solid. Now, the physics tells us that should happen, but we can work out the depth where that happens based on our observations from seismometers. So, geophysicists studied seismic waves to work out the interior structure of the Earth, and from that figured out that we've got this inner core which is solid. Not only that, the composition of the core determines the speed that the waves have travelled through the core, and because we can measure time delays for our seismic waves arriving, we can use that to determine the density and therefore the material composition beneath our feet. So this is a part of what geologists have done to work out that we've got solid iron and nickel core, liquid iron and nickel outer core, a mostly silica-based rock mantle, which is mostly solid, and then a crust around the outside of that. And that's all I have to say about seismic waves. There's probably much more I could say, but I will leave it there. So hopefully you found that useful. We are well into the course now. Where are we up to? Let's have a look. That is more than 3/4 of the way through the course of videos. Video 13 will be coming out all about the electromagnetic spectrum. If you found these helpful, great. Let me know. Drop a comment. All that sort of thing is helpful for me to let me know how you're finding it. Thank you for tuning in and watching. I do hope you found it helpful. If you are interested in taking part in those weekly tuition sessions, which are interactive, not like this at all, they are interactive, then just go to physicswithkeith.com. The link is in this QR code here. Just go to physicswithkeith.com, have a little look, see if that's something that you would find helpful. Until next time.